So make sure you've signed up for this day, next day, or the day after that. I'm glad people did listen and people are here, attentive, so I don't have to ask all the questions.
Yeah, please don't let him ask the question.
Yeah.
With us today.
Are you going to present today too? Okay, so you want to be, I want to be second. You want to be fourth?
I'll be third.
Okay, you'll be fourth. Okay, so we got 75 minutes. We have basically like 15 minutes per presentation, and then we got to switch. So
Okay.
presentation will be like 12 minutes. I'll set the time for about 12 minutes, and then we'll have a few minutes of questions. Right, so that's 4 times 15 is 60. All right, 13 minutes. 13 minutes of our presentation. We'll have like 4 minutes for questions. We do have to be careful, so the last person doesn't have to give their presentation in 5 minutes. All right, so I posted office hours today, 12:30, and I'll be here on Wednesday and Thursday. If people could bring their laptops next time, is that possible? I want to do the CIOS evaluations in class. CIOS evaluations, that's like how you guys give me a grade. And also how the class is structured. We'll do that in class, and we'll do a handwritten, we'll do like a letter for comments, and we'll do the class picture. So, and I'll send everyone a class picture.
Is that
Cool.
or is that Wednesday?
We'll do it Wednesday because I didn't give you any heads up if you didn't want to wear what you did for the class picture. And then I'll give you some feedback. And remember, the homework is due. You know, Wednesday we're gonna have a nice project on the boat problem, escaping the vortex. So the homework we do a little bit after that. So you'll get some hints on that. Well, otherwise the homework's due this Friday. I think that's it. Any other questions? I'll try to give you some like 2-minute warning. And I also have to take notes on this stuff. All right, so one of you is gonna take this, right?
Yeah, you're gonna just put it there. Because I would.
Okay.
All right, let's do it.
So we're just going to show you a real brief demo on the Schlieren effect itself, which, there we go. As you can see, basically what you're seeing is the density gradient change because of the heat. So you're visualizing the airflow, and that's the basic thing that we used. He didn't turn around fast enough. We'll have to do it again later. All right. So I'm Don McCall. This is my partner, Calvin Au. Today we're going to talk about using the Schlieren imaging to visualize fluid flows. Let's see if I can. All right. The purpose of this project was to design and build a Schlieren photography setup we could use to visualize and study various different fluid flows. Specifically, we worked to capture imagery of a levitating ping pong ball and the flow around that sphere, as well as the characteristic flow around different lift devices or airfoils. To begin with, let me talk a little bit about the camera and the Schlieren effect itself. Schlieren imaging is attributed to a German physicist, August Toepler. Oddly enough, he didn't name it after himself. Schlieren just basically means schmear or streak in German. He used it to help detect imperfection in optical quality glass for mirrors and for telescopes and stuff like that. To see these Schlieren that you can't see with the naked eye. It can be used to make visible density variations due to heat, cold, acoustics, material properties. Different gases and stuff have different densities and show up differently. It's used in a wide variety of applications, including acoustics, flow control, ballistics, and aeronautics. The way it works is by passing a beam of collimated light through some transparent substance, in our case, air or CO2, and then reflecting it back via a convex mirror to its focal point, where it's blocked by a knife edge. Any changes in density in the air are going to cause the light to be refracted, and some of that light is going to make it past that knife edge and impinge on the camera lens directly behind it. And that will show up as light in dark areas caused by the positive and negative density gradients in the fluid. There are several variations of Slurian photography. Some use lenses, multiple lenses. Some of them use mirrors in a Z configuration. But we use the Topler single field mirror arrangement with a 150 millimeter diameter convex mirror right there, and a focal length of 300 millimeters to try to keep the size and expense of the thing manageable. We drove a bright white LED via a 9-volt battery and resistor circuit as our light source, and our knife edge was a simple single-sided razor blade. Our camera is just an old Apple iPhone 6S. Used the iPhone partially because I had one, but also you have to have some significant downward exposure control on whatever camera you're using, because you got to ensure that the light and dark areas are well contrasted. And the Apple iPhones, even the old ones, do that pretty well. This is what the Slurian camera setup looks like. Most of the mountings were designed in Fusion 360 and then printed on my Creality Ender 3D printer. We attached everything to a piece of aluminum that I had around to make it easy to consistently get correct distance and angles between the mirror, the light source, and the camera lens. And this next slide just shows a blueprint of the setup with some specifications and dimensions. Let me move on to the ping pong ball section of this talk. We were interested in the Coanda effect and how it contributed to levitating a ping pong ball in a mostly vertical stream of air. The Coanda effect is the tendency of a stream of air to attach and follow a flat or curved surface brought near to it, or it brought near to that. It's caused by the viscosity of the jet entraining the existing air near the surface and causing it to move away with the jet from the surface. That resulting lower pressure area causes a net pressure force above the jet that pushes the jet toward the surface, where it can then attach. And it'll follow that surface even as it curves, so long as the curve is not too abrupt for the flow velocity. Yeah, I'm a little bit embarrassed about this, but I'll get over it. This is my poor man's graphic designer take on what a 2D ping pong ball flow should look like and the various forces at work. I note that since we can't discount viscosity anymore because the effect requires viscosity, you're probably going to have to go back to the Navier-Stokes equations and rederive a governing equation that includes viscosity, or use a force balance approach, something like that. As part of this project, we got a lot of video to try to capture some good examples of the effects we were studying. At the top right, you can see an attempt to generate a visible flow using cold air generated by a can of compressed air that you'd use to like clean your keyboard. We also tried using a CO2 cartridge. But in both cases, the flow was way too turbulent to give a good visualization of the flow patterns. But it does show how strong an effect you can get using a negative temperature differential. You don't have to use heat. You had asked about that, about bringing ice in. So same kind of thought. On the bottom left is footage of the Coanda effect radially keeping a ping pong ball captured in an airflow that we angled to demonstrate the effect working to balance the effect of gravity. You can see pretty clearly the stream wrapping around the curvature of the ball, which is the effect, especially down at the lower edge, and the effect continually pushing the ball back toward its equilibrium position, which is going to be based on the angle of flow, how heavy the ball is, that sort of thing. On the bottom right is earlier footage of a completely vertical airflow and the same sphere captured in the stream. It's really blurry, but I want you to note how the ball seems to be drawn down and toward the left of the stream. And the reason that the sphere in the vertically oriented stream favored the lower left is due to the Magnus effect we talked about in class. You can't see it in the video, but the uneven flow characteristics and the angle of attack of the hairdryer caused the ball to generate a really rapid topspin. And so its equilibrium position shifts downward and toward the direction of spin. Before that spin, the ball, and we had that going in slow motion, but before we put the spin on it, the ball was all over the place. It was very hard to capture any kind of information at all. So we actually encourage the spin to generate some stability in the position of the ball. The last thing I want to talk about is the still capture on the right, which we managed to capture the beginning of flow entrainment as we just started the flow. And that's all I got for balls. Let me turn it over to Calvin. He's going to talk about wings.
So other than the ball that we talked about, we also explore the flow around the wings. Just some background. So how does aircraft generate lift? It's just because of the wing, and it's based on either the Bernoulli's principle at the low Reynolds number and their flow circulation. That can explain a little bit more afterwards. The wings usually have thicker top and the thinner bottom, so that the flow accelerates when it goes through the thicker top, and if pressure would drop when it goes through. And everything starts from the Navier-Stokes equation, and we can take the Euler's equations, conservative force, and rotational flow to obtain the Bernoulli's principle, but that only works for the low Reynolds number flow. Another description of the flow and how it generates lift is by circulation, just like what we got in class. The circulation is just the line integral of velocity on the 2D surface of the airfoil, and the lift is generated by the negative of the air density times the flow density and times the circulation. In order for a wing to generate lift, we can see that at the bottom left corner, most point on the surface of the airfoil have a velocity component pointing downwards, and by the conservation of momentum, the air goes downward, and then there will be a lift pushing the wing upwards. And in order to test out the flow around a wing, we've 3D printed the lift devices using a Don's 3D printer. The Reynolds number on the airfoil is around 80,000, and which is pretty typical for airfoils, but it's in the turbulent region. Is there a way to deal with turbulent flow? Yes, if we use Reynolds decomposition by taking the mean of the velocity, we can simplify the Navier-Stokes equation to obtain a solution. So this is the NECA airfoil that we used for our experiment. All we need to care about is the first digit, which is the mass camber. That means how asymmetric the wing is. And I just made the model in Fusion 360 before we print it out. And this is the symmetric wing. When we test our wing, we have a hair dryer pointing towards it. And as you can see, in neutral position, there is no circulation around the airfoil, but when we increase the angle of attack, the flow starts to curve towards the tail of the wing, but at extreme angles, we can see the stall behavior. Same thing for the cambered wing, except for this time, we can observe circulation even at neutral angles. So we can see that the air actually curves downward here. So we can conclude that there is actually a lift going on here. And at a really high angle of attack, we can also see the stall behavior, but this one is much more milder than the previous one, and I will explain a little bit more later. So here are our observations. So first, the flow, it follows the convex surface, just like what Don mentioned about the Coanda effect. And the upper flow, I'm pretty sure that it travels faster, but it can be a little bit hard to see just because the flow is turbulent. At extreme angle, we can observe the stall. And all these indicates that the upper flow has lower pressure, and the viscous effect causes the flow detachment. And the lift coefficient, the higher camber will lead to a higher lift just because of the curvature of the upper surface that leads the flow to curve downwards. and the larger camber will lead to a larger lift at the same angle of attack. And you may wonder why we have a drop of the lift at the end of the curve on your bottom left corner, and that's because of those stall characteristics. And as you can see here, the more symmetric wing will have a more balanced stall characteristic. So the high circulation behind the wing at extreme angles would cause the flow separation, and that's how we lose our lift. And for the symmetric wing, it will have a thinner top, so when the flow detached from it, it pretty much detached from most of it. And all right, so 2 pages. And so here is the summary, and I would just go over to the applications. So this device allows us to visualize the wing flow with affordable and portable equipment, and is a non-invasive way to measure our flow without putting any sort of sensor or altering much of the air property. And I will bring it back to Don for the discussion.
Yeah, real quickly, we had some challenges with the camera functions and mirror quality. The mirror in our setup is just not optically consistent. It's got hot spots and stuff like that that are very hard to get rid of, so it obscures the view. We borrowed a better quality mirror that helped a lot, but it's got a really long focal length, so it required like 5 to 6 feet of space. And it's got a fiddle factor that is not linearly associated with the focal length. I won't say exponential, but it got really bad really fast. So the iPhone was adequate for exposure control, but it's often hard to get a clear video with the lack of full manual focus. So you get a lot of blurring in these videos. I will stop and.
All right, we got 3 minutes for questions. All right. I couldn't, you said that there's circulation, but I can't see the circulation. Maybe you could go show that video one more time and point us. I know the symmetric one, you don't expect circulation,
So I guess first of all, the definition of circulation is not necessarily like a circling pattern, but we can definitely see that the flow is banding, and the banding of it.
you see need the U dot DL to be non-zero around the curve, right?
Yep.
So what do you like? What do you say there's circulation? What do you see? And you can pause it.
So if we look at their velocity here, I'm pretty sure that their flow tries to attach to the surface and follow around the surface. And if we do their dot product of their flow velocity and the surface, since we have an asymmetric surface here, if you multiply that by the normal of their surface, I think you get more of velocity on the top, and you get a lower pressure on the bottom, and circulation.
Is there something about the direction of the wake that you say that there's circulation, or are you just saying there should be circulation? These are how airplanes are shaped.
I mean, if there is no circulation, there won't be any flow bending downwards. So that's what I know.
Yeah, it's really hard to visualize on the.
Is the flow bending downwards?
Yeah.
I'm taking too much time. Any other questions? Yeah.
Way back in the beginning, you guys mentioned that there are like different ways to, I guess, capture this effect using different like mirror setups. So are there any benefits to using a different mirror setup than what you actually use?
There is, but the expense and the fiddliness throws it out. They have a Z setup where you basically have 2 mirrors. You have your light source bend off the first mirror, and instead of coming back to its focal point at where the light source was, you angle it slightly, it hits another mirror, and then shoots into the lens over here. And that helps because I forget exactly what the deal is, but you don't get as the double image that you get when you have it directly in the whatever you're studying directly impinging between the mirror and the camera.
Io, why don't you come sit up and these two can continue answer questions. You just go.
So is this what's the effect called that images that visualizes the flow field?
Schlieren,
Is that what happens in like mirages as well?
I don't know,
I think so.
but yeah, it's entirely possible.
Temperature gradient.
Yeah,
See but you don't need a razor blade to see it.
no. And in fact, this is only one way to do that. There's actually another thing that doesn't use a razor blade, very similar to this, where the light goes directly into your camera lens. It's called shadowography, something like that. If you don't block the light, it's shadowography. If you do block it, it's the Schlieren effect. And he wasn't the first person to figure this out. I mean, Hooke saw this back in the 1600s, but he was the first one that used it to some effect.
I'll just leave it in there. What are all those, so pretty much all these nodes were not laminate, they were turbulent. What was around some?
Yeah, you can see a little bit of laminarization when it first comes out of the hair dryer, but it rapidly turns sugar. And that was one of the limitations of beside the mirror and the camera. I started designing a variable speed, variable temperature fan based on like a computer fan and some of that hex material that you've got. Use some nichrome wire to heat the air as it goes
I
through.
can see the lines associated. But
Yeah.
did it make it laminar or not? It needs to be really long, I think.
Yeah,
I think the speed is really.
well,
Your Reynolds number, do you know what your Reynolds number is?
we do not.
Okay. Your speed is what?
Well, that's what I didn't know, which is why we couldn't figure out the laminar.
We
I
guess
mean,
around 24 or something.
Yeah.
Oh, around.
Yeah, a lot of these hair dryers have a CFM of like between 26 and 35
Cubic
feet per minute, yeah.
The Reynolds number is mostly at the turbulence level, just because it's just easy to get turbulent flow at 20 centimeters per second. You need to get like, I don't know, maybe just several meters per second.
Yeah, same.
Do you think you'll see like better effects with the larger?
Well, it's not so much the size, I mean, it is somewhat the size, because especially if you don't have a SLR or some sort of cameras, you've got an optical telephoto. Your digital telephoto, you lose a lot of resolution when you blow it up. And the longer your focal length, the smaller your image is. So that was the other problem with the longer focal length thing, was you really couldn't tell what was going on until you blew it up. But if you blew it up, you couldn't control the light. You couldn't dumb it down enough so that you could actually see the effect. So yeah, the more optically correct mirror makes a big difference. Thank you.
Like right here? Oh. Okay. Also, can we do a sound check? Because mine is with Claire.
Yeah.
Hey, can you hear me?
Okay. Hi, everyone. I'm Io Pierce Walker, and I did this project with Claire Zwack. We're studying, where we did our project on Taylor columns, how they work, how they form, and why that's important for processes in nature. So I'm going to go over very quickly just what are Taylor columns. basically, it's the formation of a two-dimensional flow in a uniformly rotating fluid. These are maintained even when you have an object in the fluid that's obstructing the flow. So right here, if you imagine that the flow is rotating, and we have the cylinder right here, even though there's nothing actually above the cylinder, the flow will still follow the shape of the cylinder. And that creates this column of water where it's sort of stationary or relatively stationary compared to the rotation that's happening outside of it. And here also you can see the photo right there of an experiment that was done at UCLA, where they created a Taylor column. And so you see that the flow is following the shape of this object, even though the object is only at the bottom of the thing, of the container. Why does this happen? I'm going to go over the derivation because it's a really, really easy derivation. You start off with a Navier-Stokes equation and you add the Coriolis force to it. The Coriolis force is the -2 omega across U. And we all know the Navier-Stokes equation at this point. And you make a whole bunch of assumptions. For the simplest case where you can get Taylor columns, you assume that there's a steady state. Oh, you assume that there's a steady state. So the du dt term is gone. It's homogeneous. It's incompressible. That gets rid of other stuff. And then you also assume that the Rossby number, which is basically just the ratio of the inertial term to the Coriolis force, you assume that that's much less than 1. And so that gets rid of the u dot del u. And then you take the curl of the entire thing. That's going to get rid of the pressure right there, or the gradient of the pressure. And you get what we call the Taylor-Perelman theorem. That says that omega dot del u is equal to 0. If you imagine that the flow is moving only in the XY direction, then that means that you're not going to get really any change in the XY direction. And you're also not going to get any change in the Z direction because of the omega part. Yeah, there is. Right, so I think this is the video. Oh, wait,
Push play.
is this Claire?
Sure, I can talk about this video. So this video describes more about the setup that we were trying to mimic with our demo that we'll show shortly. And it talks briefly about how columns are formed and why that happens. And then it talks about the specific equipment that they used and shows the column formation. Yeah, so for our experiment, we did something very similar. We had a fluid container with our object at the bottom with a thinner layer of fluid. We used water. And then we had multiple different dyes we used. And we also were filming our videos with an iPhone camera. And then in order to induce the flow, we also used a record player similar to this video.
Right, oh, and I can show them that. So this is our setup right here.
Yeah, this is our setup. So we had a piece of foam on top of the record player so that there was a flat surface. And then we actually ended up trying to use a few different obstacles, I guess you could call them, to put in the water, but the one that worked the best was the oval shaped stone that's shown in the image on the right. We also used blue and red food dye. And in order to actually film it, we put a piece of glass over the container to place the foam as it was spinning to record the video. And one thing to note is that we set the speed of the record player to 45 rotations per minute, but it might have been slightly slower due to the weight of the objects on the record player. But that's something that we learned as we went through our experiment. And I'll just talk briefly now about some of these other lessons that we learned. So one of the first obstacles that we ran into is that we were trying to find a good object to put in the water, one that wasn't so large that it was too heavy for the record player to turn, but one that wasn't so small that you couldn't see the influence on the surrounding water as it was rotating. So we played around with some different objects, and we eventually came upon the stone that was shown on the previous slide. Another obstacle we faced is that we had to find a water container that wasn't too heavy, and we also were limited with how much water we could use because the record player wasn't a super strong, I guess. It couldn't support the weight, so it would turn much slower with more weight on it, which wasn't ideal for this experiment. And then some of the other things we learned, we had to confirm that we actually were seeing the Taylor column formation. So we did a brief check before we did our videos, which we'll be seeing in our next slide. And we did this by placing a floating object on the water, and we let the record player spin, and we waited to see if the floating object would hover almost around the stone to confirm the column formation. And then one last thing we learned is that it was more ideal to place the dye drops closer to the water surface, because we found that if we placed them higher up, that they would splash as they hit the water surface and didn't necessarily reflect the column formation that we were trying to see. So this slide here, you can see our floating object was a Connect 4 chip. And as the record player is spinning, the chip isn't quite over the stone yet, but as the column forms, it'll go towards over the stone to confirm that the fluid was acting as a rigid body and that there was in fact a column. And one thing that was interesting that we noted was, you can see it a little bit, the oscillation. Sorry. The oscillation of the chip over the stone. That wasn't something that we had necessarily expected. But it might have been due to some of some of the aspects of our setup.
Hey, Claire?
Yeah.
Oh, just we can hear you mostly, but make sure you keep your head facing toward the mic. Basically, when you move your head, it kind of turns in and out.
Okay, is this better?
Yeah, just try to just don't move.
Okay.
Well, Craig, did you ask a question? Okay.
And so this video here, we're going to show where we're spinning the record player, and then we placed the die as it was spinning to make sure that the column was already formed before we placed the die in. But as the video progresses, you'll see a column does form, but it's not completely stable. And it may just be due to either the shape of the object being an oval, or the fact that the record player was skipping a little bit and didn't necessarily rotate as steadily as would have been ideal. And then that's just when the record player stopped spinning at the end there. And we have two videos here. So the blue die is placed outside the stone, and the red die is placed inside the stone, or on top of the stone, I should say. And this was just to, again, confirm that there is a column being formed, and to show the difference between the flow on the outside and the top of the stone. So as you can see here, the blue is going around the stone, but the red continues to stay, for the most part, on top of the stone. And similar to the video with the Connect 4 chip, we were seeing that oscillation. And then the second video we're showing here, the die was placed before the record player started spinning, so slightly different than the video we just showed, but again, we saw a similar result that most of the red die stays on top of the stone.
Right. So just to review what happened, we did 2 minutes. Cool. We did see that the flow was not quite moving as a solid body. That's how we saw those oscillations. That might have been due to, say, the weight, or because as in like maybe the weight was not quite centered, or maybe the rotation wasn't perfect. And so the necessary conditions for a complete Taylor column were not satisfied. Basically, the left side of this equation probably didn't equal 0, which means that we weren't actually dealing with a low Rossby number flow. There is some evidence that there was some column-like behavior, because we saw that the die within the radius of the stone was not actually really moving, but outside of the stone it was. But it was probably like a very weak Taylor column, or something that was approximately a Taylor column. And then these are some examples in nature that we'll go over real quick.
Yeah, so we have 3 quick examples of Taylor columns in nature and current research that's being done around them. So this example here is about a seamount, which is pretty much exactly what it sounds like. It's a mountain or a hill in bodies of water. But Taylor columns are commonly found around seamounts, but they're hard to observe due to just changes in the water conditions. So for the paper that we looked at, researchers were able to describe and observe a Taylor column around what's called the C4 seamount in the tropical Western Pacific Ocean. And based on their work, researchers also conclude that the high biodiversity and amounts of animals and plants and levels of nutrients found around seamounts may be due to the water conditions from Taylor columns.
All right, and I'll speed through these last 2 examples. There in the 1960s, there was research that was implying that the big red dot on Jupiter might be a huge Taylor column that's forming due to like differences in air pressure deeper into the atmosphere. And so they go through the derivation in that paper, or in those papers. And I thought that was an interesting thing. There hasn't been a lot of recent research on their big red spot, but I thought that was an interesting example of a Taylor column. More recently, in 2020, we found evidence of Taylor columns on Europa. That's one of Jupiter's moons. These are Taylor columns that are globally distributed latitudinally throughout Europa's subsurface ocean. I don't know if you can see it here, or if the people right on here, all of these lines are where we think Taylor columns would form, sort of latitudinally. This can act as a mechanism for heat transport from geothermal heating at the ocean bottom to the ice-ocean interface. If you don't know, Europa has an ice shell, and underneath that ice shell is the ocean. So it might be a way to transport heat from the bottom of the ocean to the top. It could also imply that the ice shell thickness is uniform based on the transfer of heat and also salinity, that's salt. There's a lot of interesting things with salinity that and I do in my own research on Europa, with like how salinity can affect the way that the actual surface actually evolves. And this is just a conclusion of everything that we looked at. We now know what Taylor columns are. We know that they can play a lot of important roles in oceans. They also can play important roles in atmospheres of planets. And we found in our experiment that we couldn't really get a stable Taylor column, probably because the Rossby number wasn't low enough, and it resulted in a more turbulent flow.
We have 2 minutes for questions. One of the next group come set up while we ask a couple of questions.
Yeah. Did you look at different spinning rates on the?
Yeah, we did look at 2 spinning rates. We started off with Claire, what was it? Was it like 30 or something RPM?
Yeah, it was 33 RPM, which was what was used in the UCLA video, but since our setup was so heavy, we thought it wasn't actually spinning at the 33 RPM. So we bumped it up to the next setting, which was 45 RPM. And there was an option for 75 RPM, but the record player seemed like it was going to die if we did that for too long. So we just stuck with 45.
I was just curious, like, if you knew the effect of different spinning rates on the Taylor columns as well. Like, in theory, if record player was gonna go higher, what it would look like.
Yeah, there absolutely is an effect. We didn't study that effect, but like the Europa paper absolutely did study that effect. Looking at how the speed of the Taylor columns might influence how often they form, how close they form, and how that would affect the heat transport. You just need basically for speed, you basically just need a speed that's fast enough to get in rotating as a rigid body. So that's what we tried to do here.
So the water stationary above the obstacle, huh?
Relatively stationary, yeah.
Yeah, why, what is that? How does that arise from this, this 2 omega cross U term?
Right, so what happens is at the very bottom, you have, obviously the water is going to deform around the object, right? And we find that due to the Taylor-Perelman theorem, that relationship is going to stay even perpendicular, or not perpendicular, even parallel to the axis of rotation everywhere parallel to it. So even above it, you're still going to get that that the rotation, that it goes around where the object, where the water thinks the object is, and that a consequence of that is that the, you won't get a lot of flow above the object.
Okay, good. So we got 32 minutes for the 2 presentations. So I'm gonna set the timer for 11 minutes, 11, 12 minutes, and then you'll have 3 minutes questions, and then you guys will set up right at, like during the Q&A.
The reason why we can't see the presentation on the back screen, but not the front screens here? Is there a button I need to press? Turn what off? Oh, okay. There's just on and off. Okay. Yeah. Good morning, everyone. My name is Daniel. Today we're going to be talking about capillary waves and the dispersion relationship, which is something we kind of covered in class. In terms of how this presentation is going to play out, there's going to be a 5-minute video introducing with a quick skit of an introduction, some background information, how the math is going to work out, and then the experiment itself. And then we'll jump back to the slides. We'll do some analysis on that experiment and then talk about some future work and considerations. So here is the video.
My name is Daniel. Today,
is there a way I can turn this up, or this is what we're working with? No, she's 100%. That's okay. We can run it like this.
Hey, Jeremy, can you make the volume higher? Just try playing it. We'll figure it out.
Okay. Oh, shit. Oh, shoot.
hello, everyone. My name is Daniel. Today, we are at Georgia Tech, and we'll be talking about fluids. There are many types of fluids, from a more physical breeding to even light waves. Saint, what do you think about waves?
Not just any kind of waves.
Saint, what are you talking about?
This is fluids.
So, Saint, what do we know about waves?
There are several different types of waves in the world around us, from things such as electromagnetic waves, sound waves, to that on the surface of the water.
That's probably the most common type of waves that we can see in our own lives. When I'm on the beach or by the river, when I'm standing next to a pool during a rainstorm, I see waves appear on the surface of the water.
The waves produced by the impact of rain on a water surface will be the capillary wave. With our knowledge of fluid mechanics, we can actually articulate the nature of these kinds of waves.
Well, why don't we give this a shot for our audience's sake?
All right, let's do it. Capillary waves in fluids are mechanical waves, which means it requires a medium to propagate. In this case, a fluid, which when disturbed, generates waves along the surface due to the fluid's surface tension and pressure differences. So let's take a look at a little bit of what we discussed in class. In lecture, we talk about the linearization of small amplitude water waves with the function eta of x of t and the scalar function phi. By substitution and the enforcement of boundary conditions, we can obtain the dispersion relation, C, which is a function of k. For shallow waters, this relation is simplified to C equals square root of g over k, where C is the phase speed, g is acceleration of gravity, and k is the length number. Now that we've looked at what we discussed in class, let's look at what a textbook said, in particular, the Waves and Fluids textbook. The Waves and Fluids textbook has a section on water waves. Looking at the sinusoidal waves on water of arbitrary but uniform depth, we can derive an equation using a similar process done in class, but this time for frequency, where omega squared equals g times k times tan h of k times h. This phase or wave speed comes out to be c equals omega over k, which is the square root of tan h times h times k with g divided by g times k. With an equation for wave speed at uniform depth and a wave speed at shallow depth, let's try to set up an experiment to see whether or not these equations match up to reality. Available on hand is a large acrylic box capable of holding water. We can set up a capillary wave experiment by creating a surface ripple with an object. And in an effort to try to be original, we can run this experiment with two different round objects, a ping pong ball and a pool ball, in order to generate our capillary waves, as their different sizes and weights. By measuring the wavelength of the waves as well as the height of the water and the speed of the wave as it passes by, we can measure what is occurring in our experimental setup and see how it matches it.
In this experiment, we filled up a large acrylic box with the intent of dropping the two different spheres into the system to create a measurable ripple. Here are the results of said experiment in its raw form. This first video covers a single test of the ping pong ball wave. The second video covers a single test of the pool ball capillary wave. Using slow motion imaging, we can calculate the velocity of the wave by taking its distance over time across 2 points.
All right, that concludes the first half of that presentation. I think I'm hearing myself twice, but that's okay. It makes me sound cooler. All right, to get into how we decided to articulate the measurements of speeds and wavelength, first thing we did was take a look at that slow motion video of the two different tests, one with the ping pong ball and one with the pool ball. How we measured the speed of the wave was like across the slow motion video, we went frame by frame to try to see and look for the peaks of the waves as it moves across that tape measure underneath the acrylic box, and observed how light was disturbed, or how the the image of the tape measure and its measurements were disturbed to describe that as a peak in a wavelength and watched as that wave passed over the tape measure. So within the slow motion video, which is in the appendix of our slides, we can see as the wave moves across the surface of the water, it disturbs light that is taken from that camera and changes the image of the tape measure. So with that information, we can go frame by frame. At what points will the wave pass across certain points? And we did the math through there. Analyzing and then in order to get the wave number, we did the same thing, except looking at what a single frame and looking at, what are our different peaks in regards to those significant light disturbances across the tape measure. And as you see within our image, I'm going to use my mouse here, at around about 12 and around about 8.75 is our two significant disturbances. And from that information, we can articulate our wave number. With the calculations described in the math section, we came up with significant differences between the measured speed and the calculated speed of the wave as between 30 and 40%. And, given reflecting on our experiment, we could definitely have a better and more stronger, consistent experimental setup. The acrylic box was leaking a bit because it's kind of old. And although we used a lot of duct tape, we couldn't really get out of the fact that, we had to refill the box up to make sure it was within like 0.5 inches of its original height. It was leaking about like a half an inch per 20 minutes. We could have a better diagnostic system. Using the disturbances of light to measure peaks and wavelengths or peaks of the wave probably isn't the best idea. But when we tried to go like in perpendicular to the wave, we couldn't really get a good enough angle to where we could best articulate what was going on. And we can also have some considerations for non-gravity capillary waves and the surface tension, which I did do a couple calculations for. It didn't seem like it made too much of a difference, but it's something that could be investigated further. To kind of conclude this conversation, wave propagation and capillary waves are pretty important when it comes to understanding, wave speeds, especially in ocean development. We didn't really see much variation in speeds with different water depths or different spherical wave generators, in our case, a ping pong ball and or a pool ball. And at the very least, the precision of the calculations seems to be pretty consistent across all of our experiences. So unless there's no other questions, my recommendation is don't get kicked into a pool on a Monday morning. And thanks for listening to our presentation. Questions, comments, solutions to world peace? We're taking all and any answers.
How did you want to use the ping pong ball and is it the size?
They were different sizes and different weights. It was also what we had on hand in terms of something spherical and consistent within the CNES lab. There were a lot of screws and electrical stuff in the CNES lab. There weren't really spherical objects in the CNES lab. So that's what we had to work with.
So does the bigger object generates longer waves, and longer waves should be faster, right? Because they have shorter wave number, right?
I did one calculation, and in terms of how I measured the speed via the video, it didn't seem like there was much of a difference because like if we based on how I did the calculations with frame data and I calculated very similar wavelengths.
Other questions?
And you said I'm sorry, you said there wasn't a big difference in calculations if you lowered the water depth?
Yeah, I didn't see much of a difference, although I could have had a longer range. I think our variations of water depth was like about an inch. Yeah, you guys can come through.
I'll set up for sure.
And the question was, were there any significant variations in water depth? The textbook, Waves and Fluids, talked a little bit about depth. I think that the depth, if we look at our equation here, the dispersion relation here on the slide before it disappears, You can see that H, which represents the water depth, is tied to that tan H, and at significantly lower KH values of less than 1, it's not very significant. Yeah. There are no further questions. Me and State would like to thank everyone for listening to our presentation and watching me get kicked into a pool. And until next time, everyone. Yeah. And if you guys need help setting up, I did it, so you got it.
So you have, as they spread, like I saw there's different wavelengths and they all go at different speeds, basically, right?
It's not really something I looked too extensively at. We have the footage and videos of a couple of tests. We can take a look at that again. But in regards to like how each, like wave number 1 versus wave number 2 and how they act differently, realize that we can definitely measure the speeds of those different waves using the same method I just used. But in terms of like the wavelengths, we need wave 1 and wave 2 to measure that wavelength.
Smaller ones went faster, I saw, like those ones that are very, very small wavelength, they kind of reach the edge faster.
Yeah, that's something we can take a look at in the future. Another thing, about our experimental setup was that, when we dropped a ball, a spherical object into our fluid, it created a splash, which added droplets to the system. That might be, so in the future, we'd figure out a more consistent wave generator system, like maybe a pushing wave or maybe not just a falling object that induced a significant splash profile. But yeah, thanks for the questions.
Thank you.
Okay, good news is we have 18 minutes here, so you don't have to, there's only 4 presentations, right?
Yeah, 24 presentations.
Okay. Raphael, Gaetan, and Alex, take it away.
Okay, so hi everyone. So if you remember last time we talked about the coffee spill effect, and as we are great coffee lovers, we wanted to make our final project on the coffee ring effect. And to explain this effect to you, we did a 4 hours video that we accelerate an experiment on a drying drop of coffee. And as you can see, you see a ring that surrounds the stain of coffee after the drop disappears, and that's the coffee ring effect. So first we are going to explain the theory of this effect, then show our experiments and our results, see how we can prevent from this effect, and see finally industrial applications.
So to provide a physical description of the coffee ring effect, I would start by describing the coffee droplet model that we used. So the first condition of this model is that the contact lines of the droplets are pinned. So it means that the radius is going to stay constant over time and that the edges are fixed. So as you all know, when you pour some liquid on a surface, there is some evaporation. So this is basically what is at stake for the coffee ring effect. And we can introduce the evaporation flux, J of R. This flux is proportional to surface area. So I will now talk a bit about surface area. So on this slide, you can see in the bold blue lines, the several surface areas. And for the same small variation of radius, you can see that it is way bigger, way longer at the edges of the droplet than at the middle. So it means that there is more evaporation at the edges of the droplets. So you could expect the droplet to look like this, and over time we could thus imagine that the droplet should look like this, since there is more evaporation on the edges. However, there is a second condition, that is that the droplet has a shape that minimizes surface tension gradients. So it would be the red shape. And the blue shape is different from this red shape. So there are these small parts in red that need to be filled. And this is what creates an outward flow inside the droplet. So this is basically what creates the coffee ring effect. So I will illustrate that with coffee. So coffee is the mixing between water and coffee particles. So the particles are the black dots. Since there is an outward flow, all the particles are gonna go on the edges of the droplet. And after some time, when the water completely evaporates, there will only be the particles that are at the edges of the droplets, and this is what will give us this ring effect. So here is a small video of the particles moving towards the edges, so that you can see it. And now I will talk a bit about equations. So as I said, the outward flow velocity is supposed to compensate the evaporation. So the velocity is proportional to this flux. And with this formula, we can basically conclude that when we are close to the edges, the velocity is higher than in the middle of the droplets. So this this corroborates the observations we make with the coffee ring.
Okay, now that we understand how the coffee ring effect, we wanted to verify what parameters are influential in this coffee ring effect. So to do so, we did two experiments. The first one, the first experiment is because we read in that in many papers that the surface and the liquid composition may influence the coffee ring effect. We wanted to verify this assumption. So we let dry different drops on different surfaces and drops of coffee with different compositions. So we have simple coffee, coffee plus oil, and coffee plus soap. Here is the result that we obtained. What we can see first is that if we focus only on the coffee drops that are pure coffee on the different surfaces that are quartz, plastic plate, and paper, we can see that the effect is different. So this shows that the surface influence the coffee ring effect, and the conclusion that we can draw of this is that when the surface is porous, the coffee ring effect is less visible. Then secondly, if we look at the rows of this table and we focus, for instance, on the first one, we can see that for different liquid, the coffee ring effect is different too. And what is interesting to notice too is that for the mix of coffee and soap, the coffee ring effect vanished. So noticing that, we did a second experiment, which is we wanted to see if the concentration in soap that we put in this liquid will change the coffee ring effect. So that's what we did in the second experiment. So here are results again. So if you follow the arrows, the concentration in soap in coffee is increased. And what we can notice is that if there is a very small amount of soap, the coffee ring effect is still very present. But as we increase the concentration in soap, the coffee ring effect vanish. And at the end, we have almost no coffee ring effect. What is interesting to notice too is that in the transition zone between the two extremes, we may notice that in the circle that we observe, as we increase the concentration of soap, it looks like we have several coffee effects appearing in the stain with different radius.
Yeah, so it seems that adding soap suppresses the coffee ring effect, and then we can ask ourselves how to prevent from the coffee ring effect. So let's go back to Alex said about the coffee ring effect, which is outward flow that pushes the particles to the edges of the drop. And we want to avoid that. Now, how can we avoid that? By putting a surface tension gradient that named Marangoni flow that will create a counterflow that will push the particles from the edges toward the apex of the drop. And when the drop will dry, actually, it will create a uniform deposition, and then you will avoid the rings on your stain. And so it will suppress the coffee ring effect. So if you go back to our experience, we have introduced Marangoni flow by adding a surfactant, which is soap. So surfactant is a substance that reduces surface tension. And in that case, as the particles are at the edge of the droplet, as they have a low surface tension, they will go to the apex of the drop, which has the high surface tension. So this is the Marangoni flow. But there is a second thing that's happening, which is that the radius, with the presence of the surfactant, the radius will decrease as long as the evaporation proceeds. And in that way, that explains why you have several coffee rings that appears on our stain of coffee with soap because of this decreasing of radius.
So to reduce the coffee ring effect, some other papers studied the influence of the shape of the suspended particles. So we couldn't do the experiment, but another paper used micrometer-sized polystyrene particles, and they tried to compare spherical shapes with ellipsoid shapes. And what you can see is that with the ellipsoid shape, so on the left, there is no more coffee ring. The coffee distribution at the end is uniform, while with spherical shapes, there is a coffee ring effect. So from what we understood from the paper, it is caused by the fact that ellipsoid particles have stronger interactions. So they pack together and they are not moving with the outward flow because they are more difficult to move. And that's why they stay evenly distributed on the droplet.
So now let's talk about some industrial application, because coffee ring effect may be a major issue on printing industry because it can cause like empty letters, and you don't want that. You want filled letters on your printing sheet. And in that way, so this is a quick video that shows how inject printing works. So you have electrical devices that deliver many drops of ink onto your paper. And to avoid coffee ring effect, well, you use two small surfactants with low density that will stay only on the surface of your drop. And as I said, it will create a Marangoni flow at the surface that will push the particles to the center of the drop, and then you will have a uniform printed letters.
So Raphael presented you an industrial application where we want to avoid the coffee ring effect, but it exists also application where we use the coffee ring effect. One of them is the malaria detection test. So here is a picture of a blood sample infected by the malaria parasite. You can see that when your blood is infected by the parasite, the shape of your blood cells is modified. And as Alex said, if we modify the shape of the particles, the effect will be different. So here is the test that some researchers are trying to elaborate now. And you can see that if you are uninfected or infected, in both cases, you will still have the coffee ring effect, but the result of this coffee ring effect would be different. And this solution is a very interesting one that they are trying to elaborate, because this will be an easy and affordable test, because you only need a blood sample and a plate of plastic. So it's really practical for a region where you don't have a lot of medical infrastructures. To conclude on our work, we presented you the coffee ring effect, which is here. So as Alex said, we need two conditions to have the coffee ring effect, which is having pinned edges, and a shape that minimizes the surface gradient. And we also presented you three solutions to avoid the coffee ring effect. The first one is changing the surface on which your drop is drying. The second one is changing the shape of your molecules. And the first one is introducing a Marangoni flow thanks to a gradient in surface tension. Thank you for your attention. And if you have any question, don't hesitate.
Questions?
Yeah, I just had a question about the last thing you talked about, the malaria detection. I didn't really understand how it works.
Oh, yes. The thing is that, as I said, if your blood is infected by the malaria, the shape of your molecule will be different. And I didn't enter in the details, but the scientist elaborated a solution which is composed of magnetic particles that, if your blood is healthy, will react with your blood cells and bond with them. And the thing is that the whole particle, which are your blood cells and the magnetic particle, will all be influenced by the Coffering effect. So they will all move till the edge. And in the opposite, if you are infected, your blood will not bond with the magnetic particle. So only your blood will be subject to the Coffering effect. And the magnetic particle will stay at the center, because on the plate that they do for the test, you have a magnet under it. You're welcome.
The coffee ring is affected by the shape of the coffee or the droplet. In case I have like a hydrophobic surface, like would that increase the magnitude of this effect?
As we tried with experiments and as the theory could say the same, if the surface is hydrophobic, they would the shape of the droplet would be different. Like the model I showed in the first place, the condition would not work. So so no, they wouldn't be a coffee ring effect if the surface is completely hydrophobic. We actually tried in experiments to pour some coffee and some scotch, some plastic surface, and it didn't work because it was hydrophobic.
Did you record?
Go ahead, Raj.
Did you record the experimental time it takes to evaporate various solutions, like the coffee plus soap? How long did it take to evaporate completely?
For the experiments that I presented, it took between 1 hour and 2 hours to be fully evaporated for all samples.
Yeah, so I'm not much of a coffee drinker myself, but I was just kind of curious if like the different types of coffee would have any effects on the actual coffee ring.
This is one thing that we studied, but we didn't present it you. But if you have a more concentrated coffee, yeah, for instance, but it's not the case here. But the thing is that if you take a more concentrated coffee, the ring would be larger. This is the influence that the concentration of coffee have, just on the thickness of the ring.
So these experiments are just very clear. So that outer edge, that's pinned, right? That's basically where you put it in and then it stays there. Well, yeah, you said the surface area, you said the evaporation is more on the edge. Why is that?
Actually, it was like in the paper we studied, they didn't give the complete formula of the evaporation flux, but they stated that it was proportional to the surface area.
I always thought drops, they're going to be some segment of a circle. So don't they all have the same curvature everywhere?
Yeah, but here you are more, if you take the same length, here you have more surface area here than here. So that's why the evaporation is higher at the edges than the center. Okay, sorry.
Okay, so it's like this.
So what I say is just you have the same, if you take those two lenses, so this is the same length, here you will have more surface area at the edges than at the center. So that's why the evaporation is higher at the edges.
Yeah, okay.
Is the evaporation flux proportional to the surfactant concentration?
I'm not sure because I mean, maybe there is a link, but the surfactants is a way to create a surface tension gradient because you reduce the surface tension. So it, in a way, it reverses the coffee ring effect. But
I think for this question, the surfactant would only change the composition of the liquid, and that would be, I think, the only change in evaporation itself. Because I think I cannot think of another way it could change evaporation.
Okay, that's time. So let's think all this together. And the next time, please bring your laptops and be prepared to set up either beginning of class or in between. I suggest you reduce your stress by trying to set up. So we'll have 1, 2, 3, 4. We'll have 5 presentations next time. So we're going to go a little bit faster. And the last day, somehow we have 6 presentations. Tomorrow, Wednesday, we'll also do the group picture and evaluations on the COS. So that also takes some time.
So leave this in your lab? I can build one.